Hi students, welcome back to science class. So chapter 10, light, reflection and refraction. So in the second part, refraction. In the first part, in the first video, we have discussed the basics of refraction. So what do you mean by refraction? So what is refractive index and what are the laws of refraction, and finally Snell's law and refraction through the glass slab. These and all we have discussed. So in this video we are going to see the refraction of light by various lenses, that is spherical lenses. So spherical lenses, there are two types of spherical lenses. One is convex lens, another one is the concave lens. So in convex lens, the both surfaces of a lens bulged outwards. So this is convex lens. So it is called converging lens because light rays after falling the lens converged at a point. So it is called converging lens. So in case of concave lens, the rays after passing through the lens, it will be diverged. So it is called a diverging lens. So it is called a diverging lens. In convex lens, so here the central part of the lens, either convex or concave, the central part of the lens will be optical center. It is called optical center, denoted by O. And the surface forms a spherical part of the sphere. So it forms a sphere. So the center will be here. So that is called the center of curvature of this lens C. So it has two surfaces, two centers of curvatures, and the distance between O and C is approximately equal to the radius of curvature. So OC equal to radius of curvature, and F2 and F1, that is, these are called principal focus of the lens, because the parallel rays passing through the lens converged at that point. That point is called focus or principal focus of the lens. So due to two surfaces, there are two focus, F1 and F2 on either side. So here this distance will be F1, OF1, and this distance is 2 F1. So this is the distance OC is twice the distance of OF. Simply OF is called focal length of the lens because it is focus at a point. So the distance between optical center and focus is called focal length F. Already we discussed focal length F, and it is the half of the distance between this distance, radius of curvature OC. So OC is the radius of curvature, capital R. So the half of the distance, half of the radius of curvature is called focal length of the lens. So this is similar to the concave lens also. So O is the optical center, F1, F2 are the principal focus or simply focus, and C1, C2 are called centers of curvature. So which is equal to 2F2. So taken as 2F2, here 2F1, and here Mn is called that is diameter of the lens, simply aperture of the lens. So if we are looking the side by the lens, so it will be like a circular outline. So like this circular outline. So the diameter is, this circular outline is called the aperture of the lens. So both are looking like circular outline. The diameter, that is here Mn, is called the aperture of the lens. So these are the basic parameters of the lens. Next we move to image formation of lenses. So in order to find the image formed by the lenses, so if you place the object in front of the lens, the image of the object will be obtained by the image formation by the lenses. So in order to find that, we need three conventional rays. So that is categorized as the three rules: ray 1, ray 2, ray 3. There are three rays are there. So by using these three rays, we can obtain the image formed by the lenses. So among three, two rays are necessary to draw the image diagram. So what are the three rays? Now we are going to discuss. The first ray is the ray parallel to the principal axis. This line is called principal axis. That is the line passing through the optical center, and focus is called the principal axis, simply axis of the lens. So the ray passes parallel to the axis. After refraction by convex lens, it passes through the principal focus of the lens. Again I am telling, the ray passes parallel to the parallel ray. After refraction, it passes through the focus. on the right side of the convex lens. The same case, in concave, the ray appears, the parallel ray after refraction, the diverged this direction, so it appears to diverge from the principal focus. So the parallel ray after refraction by the concave lens, so it appears to diverge from the principal focus. Here it actually passes through the principal focus, but here it appears to focus, it appears to diverge from focus. Second ray, that is, a ray passes through the focus after refraction, it passes through parallel to the axis. So incident ray is always taken left side of the lenses. So the incident ray, the ray passes through the principal focus of the lens, by after refraction it emerges out parallel to the principal axis. So in the case of concave, a ray, the incident ray, appears to meet at the principal focus, appears to meeting at the principal focus. After refraction it emerges parallel to the principal axis. So if this is the incident ray, it comes, it appears to meet at the point principal focus, but actually after refraction it passes parallel to the axis. So not actually meet at principal focus, it is appears to meet at principal focus. So after refraction it will pass through parallel to the principal axis. So this is second ray. So third ray is the any oblique ray, that is, a ray passes through optical center. So oblique means it may be any direction, but it passes to any angle formed with the lens. So it passes, the important thing is it should pass through the optic center. So the ray passes through the optical center, without deviation it will emerge out and it will be refracted. So the same, it is similar to the concave also. So for convex and concave, the ray passes through the optical center, without deviation it will emerge out. So these are the three rays, three rules taken to find the image formation. So again we recall it. The first ray is parallel ray passing through the convex or concave lens, it emerges out. In the case of convex, the parallel ray passes through convex lens, it passes through the principal focus. Here parallel ray after refraction, it appears to diverge from the principal focus. Second ray is a ray passes through the focus. After refraction, it passes through parallel to the axis. Here a ray appears to meet at a focus, it passes through the parallel ray. Third one is the oblique ray, that is, ray passes through the optical center, no deviation it will emerge out. So these three rays are very important to draw the ray diagram to form the images. Next we move to image formed by convex lens. So here there are different rays passing through the convex lens. So at initially we consider the ray comes from infinity. So the rays comes from infinity means parallel rays, which means the object is placed at infinity distance. So it will produce the parallel rays. So the parallel rays after refraction, after falling on the lens, it will, all rays are converged at a point. That point is called, we know, principal focus. So at the object placed at the infinity, after refraction image will be formed at the focus. So this image will be very point sized, that is highly diminished and point sized. So it is a real and inverted image. Real means we can view the image on the screen and it will be inverted. So this is the nature of the image. Here was the optical center, f1 principal focus, and 2f1 is called center of curvature. So this is the first ray. The second ray, here object is placed beyond 2f1. Here O, f1, 2f1 and infinity. So first initially we taken the object at infinity here, and second beyond 2f1. So for beyond 2f1, here object is placed, AB is the object placed. So in order to find the image formed by this lens, we have to take any two rays. We saw the three conventional rays, so we should take any two convenient rays. So first ray is parallel ray, another one is the ray passing through the optical center. First you consider the ray parallel to the principal axis. So after refraction we know it passes through the focus and extend that line. So next you draw the ray passes through the optical center. So simply we know after refraction no deviation, without deviation it will go. So you extend that line also. So both lines meeting at a point. So this point will be this point, the point image of the object. Here AB, A is the head, B is the bottom tail. So here it is, this point is called A dash. So head of the image and bottom of the image is B dash. So AB is the object, A dash, B dash is the image. So image is inverted and it is real. So real means it can be viewed on the screen. So we can obtain the ray diagram when the object is placed beyond the 2f1. So image is, here object is placed beyond 2f1. So image is obtained between f2 and 2f2. So draw the image like this. So the position is between f2 and 2f2 and nature, the size of the image is diminished. So this is AB is bigger than the A dash B dash. So diminished, somewhat diminished, and nature will be real and inverted. So here we know the distance between the object and the optical center is called object distance U. Distance between the image and the optical center OB dash is called the image distance V, and the OF, the distance from optical center and the principal focus is called the focal length. So this is the object placed beyond 2f1. So in case of, by replacing this arrow mark, by assuming a man standing in this place, so we can obtain like diagram like this. So a man is standing beyond 2f1, so we can obtain the image by using ray diagram like this. So image is obtained between f2 and 2f2. So the image will be diminished image. So the size will be, the height of the height of the object is this AB, and the height of the image is A dash B dash will be diminished, and it is real and inverted. So real and inverted. So this is second case, and we will move to third case. The object is now placed at the 2f1. First case beyond that is infinity. Second case beyond 2f1. Now 2f1. So objects are in every case closely moving towards the optical center. So now 2f1. So in order to find the image of this object, we have to same consider the two rays. First ray passing parallel to the axis. So after refraction we know it passes through the focus of the lens. So it extend that line. So second ray you taken is the ray passes through the optical center. So after refraction, no, without deviation it will go straight line. So the two rays meet at point, that point is A dash. So you can draw the extend this line as it is a image of the object A dash B dash. So here you saw at the image is formed exactly 2f2. Object is placed to 2f1, principal focus on the left side. The object also, so image also produced at the principal focus on the right side of the lens 2f2, and the size will be the same size, and nature will be real and inverted. It's a real, it can be seen on the screen, and inverted, and but size is same and distance are same, U equal to V. So easily we can find out the focal length of the lens. So this is third case. And the fourth case, so in the third case, a man is standing on 2f1, principal focus on the left side. So we can obtain the image should be principal focus of right side 2f2 image, the same size, and the object is inverted. So this is the third case. Fourth one, at D case, now object is placed between the f1 and 2f1. This is the object, AB is the A, here B, AB is the object between f1 and 2f1. So in order to find the image of this object, you take two rays, you draw the two rays. One is parallel ray, parallel to the axis. After refraction we know passes through the principal focus on the right side. So it will go like this, and a ray passing through the optical center, it without deviation it goes, and two ray meet at the point, that is A dash. You draw the image diagram of image. So it is called A dash B dash. So here the image is formed beyond the 2f2 of the right side, 2f2 beyond the right side. So object is placed to 2f1 and 2f1, and image is formed beyond the 2f2, and the size will be, relative size is enlarged compared to AB. A dash B dash is enlarged. So enlarged, and nature will be, it's a real and inverted, real and inverted. So we can view like this. So the object is placed to f1 and f1. The image will be formed at beyond 2f2. It will be enlarged image, enlarged image. And fifth case, the object is placed at the focus. Next point is focus. So AB is the object. So same two rays can be taken. So first ray parallel to the axis. So it after refraction go f2, passes through principal focus, and ray passing through the optical without deviation go like this. So both rays are parallel. So parallel rays cannot meet. Otherwise we can assume they will meet at infinity. So they will form the image at infinity. So the image will be very very enlarged, highly enlarged. So we can tabulate the values at focus, object placed focus. So image will be obtained at infinity, and the nature will be real and inverted, and the size will be highly enlarged. So infinity, it forms highly enlarged image. So this is the fifth one. The last one to move towards optical center. So the last one is, the image is placed in between f1 and optical center, f1 and optical center. So now you take the object is a small, because here previous cases we have taken all the objects are same height. The last case only you should take the object size will be small, because we have to take the virtual image. So virtual image means we can view the same side, the lens itself we can view. So in order to draw the virtual image, object should be taken small. So for conveniently we have taken small size. So here object is placed between the f1 and the optical center. So this is AB. Draw the same two ray, parallel ray. So after refraction it passes through the focus, and second ray, ray passing through the optical center, the passes through this direction. They are not parallel rays. They appears to meet at a point. So for that, in order to meet that meeting point, we have to extend the line behind the lens. So extend the both lines, both refracted rays. So dotted line shows the extension of refracted rays. So it will at a point. So these are the not real. So for imagination only. So that's why called virtual. So this image will be virtual image, A dash B dash. So the size will be enlarged, but it's a virtual and upright, straight. So it is called erect image. So virtual and erect image, and the size will be enlarged compared to the object, enlarged, and the position is behind the same side of the lens, okay, behind the object. So beyond 2f1 or f1. So this is the position of the image. So these 6 objects, 6 points are tabulated here. So at infinity, beyond 2f1 and 2f1, and between f1 and 2f1, and f1, and between f1 and the optical center. So the distance move towards the optical center, the position of the image will be away from the optical center at focus between f2 and 2f2, at 2f2, and the size also, the from highly diminished point size to diminished same size, enlarged and highly enlarged. So and first 5 cases real and inverted images we can obtain, because convex lens, the right side of the lens only we can obtain the image. So all images are real and inverted. The last case only we can obtain the virtual and erect image. Virtual means we cannot see on the screen, only we can view the lens itself, and the image will be upright, erect. Real images are always inverted, virtual images are always erect. So these are the important things we have to remind it. For concave lens, only 2 cases are there, only 2 positions are there. First position is object is placed at infinity. Infinity means the it will produce the parallel rays. So the parallel rays we know after refraction it will diverge this direction. So which means it appears to diverge from the point f1. it appears to diverge from the focus. So we have extend these lines, the diverged refracted rays, so it will meet at point focus. So the image is obtained at the focus. When the object is placed at infinity distance, the image will be produced at the focus on the same side of the concave lens. So we can draw by using this ray diagram. So it will be focused at focus, so it is a point sized, so point sized, and so this is not a real image. So after refraction it will go this direction. For convention we are extended these lines and it meet at the point f1, so it is called virtual image is always erect, upright, and it is point sized. So this is first case. Next case is any point between the infinity and focus. The object is placed in between infinity and focus of the lens or optical center of the lens, or otherwise beyond f1. So second position. First position is infinity. Object is placed as infinity. This position we can find any position between 2 f1 and optical center. For convenient we have taken here between 2 f1 and f1, that is between infinity and optical center. For convenient we have taken this here. So AB is the object. In order to find the image we have to take two rays. First ray is parallel to the axis, so parallel ray. After refraction we know in the case of concave it diverged this direction, which means in order to draw the diverged ray, emerge out ray, just you start from the focus. This, it appears to diverge from the focus. The parallel ray in case of concave lens, it appears to diverge from the focus. So for this, extend this line, so it will meet at focus. So this is first ray. For second ray always we have chosen, that is ray passes through the optical center. So after refraction it will, without deviation, it emerge out. So we can also they extend the same line on the same straight line, so it will meet at the point A dash. So two refracted ray, so this is the incident ray we know. So after refraction it will go this direction. For virtual image, just we extend the same direction. Here diverged ray is extended to the point f1. So likewise if you extend this line, it will meet at the, both two extended lines will meet at point A dash. So A dash, B dash is the image of the object. So here the object is placed between the two f1 and O. There is infinity and optic center. The image is obtained between focus and optical center. Focus and optical center. The size will be diminished. So diminished, it's virtual and erect. We cannot see on the image. We can view only the lens itself. So it is called virtual. So same ray diagram. A man is standing near the 2f2. In this diagram, we have chosen the object is placed at 2f1 and f1. We may choose any point between infinity and the optic center. For convenient we have taken beyond the f1. So here also a man is standing beyond f2, this position. So after the image will be obtained here. Okay, it's a diminished size and virtual and erect image. It's not a real image, virtual image and erect. So only two options are there in the case of concave mirror. First position is the at infinity. Second position will be at any point between the optical center and infinity. Only two positions of the objects are there. So in case of convex there are 6 positions. Among 6, 5 are real and inverted image. Last one is virtual and erect. Here both two images obtained by the concave lenses are virtual and erect. So this is the important thing we have to remind. Next, sign convention for spherical lenses. Sign convention means we know the u, v, height of the image, height of the object, and focal length. We know the u is the object distance, v is the image distance, and the height, h is the object height, and h dash is the image height, and f is the focal length. So for these 5 things, so we have to consider a sign convention. So it is similar to the spherical mirrors. The same formula are applicable to the spherical lenses. So here the distances taken from, so always object is placed left side of the image and always above the optical axis. So the object distance you use always negative. Okay, next. So it is spherical lenses, lens and mirror, the same convention. So the object always we place the left side of the lens or mirror, so the object distance u is always negative. Okay, next, the object height always its position is above the optic axis, so it is always positive. We know that simply the Cartesian coordinates xy, when it's in positive x direction it will be positive. In next situation it is taken as negative, and the positive y direction the all values are taken as positive, and the negative y direction. So this is the axis, this is the center. So the object, the distance measured the above the axis are taken as positive, so the distance measured below the axis are taken as negative, simple thing. And the object distance from the pole, right side from the pole are taken as positive. So the object distances measured from pole to left side is always taken as negative. So this is positive x direction, negative x direction, positive y direction, negative y direction. That's why we are choosing the negative positive values. So we know the u value always will be negative and h value always will be positive. And if the object is, if the image is formed right side of the lens, then v will be positive. Suppose for virtual images, so it will form on the same side, left side of the lens, so the v object image distance will always negative. At the same time, for the images, so real and inverted images, real images are inverted means it will the below the axis, so it is negative. Suppose if a virtual and erect image always the above the lens, so the height, the object image height will be the positive. So these are the conventions. So while solving the problems, it is easy to recall these sign conventions. Next, lens formula. It's similar to mirror formula. So lens formula can be obtained. So the mirror formula, lens formula is nothing but simply the relation between the object distance u, image distance v, and focal length of the lens. So there is a relation between these three. So it gives us the mirror formula and the lens formula. So just you compare two formula, then only it is easy to study. So the same magnification is nothing but how much the object can be magnified. So the image is magnified image. So magnification means how much times is bigger or shorter compared to the object. So that is called magnification. So it is taken as height of the image by height of the object, h dash by h. So for mirror formula, we know in the first lesson, first part we have discussed. So that is 1 by v plus 1 by u equal to 1 by f. For mirror, always you should take the v first. 1 by v plus 1 by u equal to 1 by f. So for lens, simply this same formula here, replacing plus, this is minus. So 1 by v minus 1 by u equal to 1 by f. The same magnification formula. So this is common to both. Height of the image h dash by h is the magnification, but in the case of lens, mirror, minus v by u. So m equal to h dash by h, which is equal to minus v by u. In the case of concave, lens, m equal to h dash by h equal to v by u. For mirrors, minus v by u. For lens, plus v by u. So simply these four formulas you should remind. First you take the mirror formula and magnification. Next lens formula, magnification. So just you remind in your mind, this is plus, minus and minus, plus. So here plus will, so plus, then minus will come here. Here plus will come, so minus will come here. So automatically it is will be plus. So 1 by v plus 1 by u equal to 1 by f equal to minus v by u plus v by u, and here is replacing plus, it is minus. So this is the lens formula and magnification. Here easily we can find out. That is, if two of the parameters given. If we are given, f we can find, or suppose if u and f are given, we can find. Suppose v and f are given, you can object image distance u can find. So the same time, so if v and u given, magnification are calculated, and h dash by h also given, magnification find. So by using these formulas, so object height will be calculated, and the image height will be calculated, and the nature of the image also be calculated. So magnification here for here for lenses, magnification equal to taken as h dash m equal to v by u. So for magnification for real images will be always negative, and magnification for the virtual image is always positive. So by solving the problems, we can easily understand these things. Next, power of the lens. Power of the lens means how much a light ray can be diverged or converged by the lens. So the degree of convergence or degree of divergence of the lens is called power of the lens. If the convex lens means the light rays can be converged. So degree of convergence of the convex lens is measured in terms of power of the lens. The same for concave lens, the degree of divergence can be measured in terms of power of the lens P. So also power of the lens is taken as reciprocal of the focal length. We know the focal length means the distance between the optical center and the focus of the lens. So focal length, the focal length of the convex lens is positive, and focal length of the concave lens is always negative. By convention we know. So power of the lens can be defined as it is the ratio or reciprocal of the focal length. So it is the SI unit of lens, power of the lens is called diopter, taken as diopter. Simply we know the focal length. Focal length is measured in terms of meter. So 1 by meter, so meter inverse. So 1 meter inverse is called as 1 diopter. So 1 diopter equal to simply 1 meter inverse. It is explained. So this is written here. 1 diopter is the power of the lens whose focal length is 1 meter. So the questions may be asked, define 1 diopter. So 1 diopter is the power of the lens whose focal length is 1 meter, which is equal to 1 diopter equal to 1 meter inverse. And the power of the convex lens is positive, and that of a concave lens is negative. We are using the spectacles. Among our students, we are using the spectacles. So we are using the different type of spectacles for depends on the problems, either myopia or hypermetropia. We are using the concave and convex lenses. So in order to correct the long sight and short sight, so if we use the convex lens, so that we know the power taking the positive 0.2, 0.5, 1, 1.52. So it has the 2 diameter, 0.5 diameter. So always positive. For concave lens, we know the power. The doctor say the power of your lens. If you are used the concave lens, so the power will be the like minus 0.5, minus 1, minus 1.5, minus 7.5, minus 0.75. So these are in diameter. Minus 0.5 diameter. So here minus means we are using the concave lens. If plus means we are using the convex lens. We know convex lenses are used to long sightedness, and that is for hypermetropia. And concave lenses are used to myopia problems, short sightedness. So we know these things we will discuss in the next chapter. So what are the uses of the lenses, and what is actual taken for consideration, that is in human eye. It's a next chapter we will discuss later. Here I am going to tell how to draw the ray diagrams. First, convex lens. So for convex lens, for either convex and concave lens, first you have to write a optical axis. So this is the optical axis or principal axis. Draw the straight line by using the scale and pencil, and after that you draw the lens for convex lens. So this is convex lens. You may use or any curved objects. For compass also you can use. So exactly the optical axis will go through the half of the lens. So just like you have to draw, and you point out the optical center O and F1. Here F1 the principal focus, and F2 F1 that is 2f1 or c1, center of the curvature, 2f1. So right side, so the same distance you have to take, same distance, OF1 equal to f1 to f1. So the same on the right side also, same distance. So this is f2 and 2f2. So you have to draw like this. And for convex lens, draw the ray diagram. First case, the object is placed in the infinity, or if you take the second case, the object is placed beyond the 2f1. So you always take like this, beyond 2f1. So this is AB. So this is the object AB. So in order to find the image, we have to take any two rays. First one is the parallel ray. For parallel ray, you have to draw the parallel. So that you have to draw the lens. Okay, you have to draw the lens. Otherwise, you have to draw like that the image. So for parallel ray passes parallel to the principal axis. So after refraction, it will pass through the principal focus. We know principal focus. So you should use the scale and pencil. So extend these lines. Okay. So this is the incident ray. After, so parallel rays are converged after refraction through the, it passes through the principal focus on the right side. So this is first ray. So you have to take second ray. So always you have to take the second ray by so second ray passes through the optical center. So the ray passes through the optical center. So it will, without deviation, it will emerge out. So you extend the same ray. So like this. So this is the incident ray passing through the optical center. Without deviation, it will emerge out. So both the two refracted rays, emerged out rays, are meet at this point. So this point is A dash. That is head of the arrow mark. And you have to draw like this. So this is the head. And this is the bottom. So this is A dash. So this is B dash. So this is the object. So the image of the object is like this. So object is placed beyond the 2f1. So image is formed between f2 and 2f2. So this is the real and inverted image. Inverted, and position will be the between the f2 and 2f2, and size will be diminished compared to the object size. It is the diminished. The same if you take the second category, if you just you draw like this. Okay, for this is O, f2 and 2f2. So this is f1 and 2f1. Okay, now you take any ray. So that is at 2f1. If you take a object placed at 2f1, so in order to find the object image, so we have to take the two rays. First one is the parallel ray. So the parallel ray parallel to the axis, after refraction it will pass through the principal focus of the lens. Second ray we should take, it passes through the optical center. So it will emerge out like this. So extend like this. So meet at this point. So approximately you have to take here. So this is this. So if you use scale and pencil and the same angles, so it is the some size will be same. So size will be same and the position will be the same, 2f2, 2f1, object is 2f1, image will be 2f2. So and the nature will be real and inverted. So this is in the case of convex. So if you take the third case, so suppose in the convex mirror, the last one we know. So this is O, f1, this is 2f1. If you take the object between the f1 and O, so it should be taken as small. So after refraction, this is f2, this is 2f2. After refraction, you should take the two rays. It will pass through the f2 and second ray passing through the optical center. So this is like this. So to find the image, so you have to extend. We have to extend. So object, the image will be here. So the object is here A. So here A, B, here A dash, B dash. So object is enlarged and behind the lens object. So So this is the last case. So this is called a virtual image, not a real image. We are extending the refracted lines. So virtual object, virtual image, and erect. So this is in case of convex. Suppose if you take the concave, so there are only two cases. So you have to draw the optical axis and you draw the convex mirror like this. Okay, so find O, F1 to F1, sorry, F2 to F2, here F1, and this is to F1. Suppose if you take any object in between 2F1 and F1, so the object will be so always virtual and direct. So the ray parallel to the axis, so emerge out, it appears to diverge from the focus. So this is the convention. So the first ray, second ray, the ray passes through the optic axis. We know you should draw like this. Okay, just you extend the same line backward, and the meeting point will be the image. So this is A, B. So this is the A dash and B dash. So this is the virtual and erect. So image formed between the optic center and F1. So this is in case of concave lenses. So these, if we use the scale and pencils, we can obtain the neat and neat diagrams we can obtain. So just you put the practice and draw various diagrams, and again and again you have to draw the diagrams, then only we can obtain the neat and clean diagram. So that we have to don't confuse with the parameters behind the lenses, and you remind the tabular columns where the object are placed and where will the image will be formed. So this and all we should know. So if you remind that things, you can draw the trade diagrams. By using it we can obtain the neat diagrams. So thank you.